We
So, welcome to the, I think, 9th ReMO seminar series. And this presentation will be given by Haichao from Geomar in Kiel about oxygen utilization rates and how they can be used or cannot be used to track the long-term changes of respiration in the mesopelagic zone. And Haichao, the screen is yours.
Thanks, Iris, and good evening, or good morning, or good afternoon to some of you. And I'm Haichao, and I'm from Juma. Today, I'm very honored to have this chance to give to share some of my recent research in this remote seminar. The topic is can oxygen utilization rates be used to track the long-term changes of aerobic respiration in the mesopelagic zone? Sorry for the quite long title. And this study is explored by my colleagues in Juma, Iris Christ, Andreas Erslis, and Wolfgang Kopf, and myself. And the manuscript has been submitted to JIL, and it is currently under review. So first, I want to introduce the motivations. There's one processes that is induced by the climate change. We call it ocean deoxygenation, which means the dissolved oxygen concentration in the ocean is declining, and that impacts a lot to the ecosystems, to the fisheries, and it might enhance the production of nitrous oxide, which is a very strong greenhouse gases. And the models try to project what the oxygen concentration will changes in the future. So the model and the IPCC models project that ocean oxygen inventory will decrease or continue to decrease, and by the end of this century, the 3 or 4% of this of global ocean oxygen content will lost. That is a very dramatic changes. But the model, unfortunately, cannot simulate the deoxygenation that observed in the past. Observations shows from 1960s to 2010s, there are 2% of total ocean oxygen inventory has been lost. But the model gives the value of 0.6 only. So the historical simulations in the models underestimate observed deoxygenation by 2 or 3 times. That is a very large uncertainties. So definitely the models, there's some mechanisms behind ocean deoxygenation. Is either not were reproduced or is not included. So we need to learn some mechanisms behind ocean deoxygenation. What is happening in the ocean? For which might impact the oxygen concentrations. So there are at least three main mechanisms behind the declining oxygen from climate change. That is the solubility trend, the ventilation changes, and the consumption, the oxygen consumption rates changes. The solubility will decrease because the increase in temperature will lead to the decrease in solubility. So the surface water is not able to uptake the oxygen as it was before. And the ventilation will perhaps also decrease because we have the enhanced stratifications. The water need more energy to go down from the surface ocean to the deep ocean. But the consumption rates of oxygen might also changes because ecosystems also respond to the climate changes. For example, the increase in temperature impacts the decay rates, and there are many other processes. But so far, at least to my knowledge, we don't have the observed long-term trend of consumption rates, how that changes. There's maybe one way, which I will introduce later, which is a geochemical way to give the proxy of the consumption rates and reconstruct the respiration rates in the past few decades. So that way is called oxygen utilization rates. We refer to OUR. So in this green box, I introduce what is OUR and how it is calculated. So the first, we calculate the apparent oxygen utilization. So that is just the difference between the saturated oxygen and the observed or measured oxygen. It gives the accumulative effects of respirations, which is from the out curves to the measured locations, how many oxygen is consumed. And then we calculate OUR by calculating the gradient of the age of AOU divided by the gradient of the age. Now the age in the real ocean is hard to get, but we have some CFCs or other radioactive traces. We can derive some ages. And then we can calculate OURs in the real ocean. It's really a proxy of the respiration rate or local respiration rate. I know that the formula is not a good way to show some concepts. So I'll give some schematic plots to introduce the concepts of OUR. So first we have the ESC gas exchange near the outcrop. So at the surface ocean, the oxygen is always there. And then if we only consider advection, this water is like a box and it moves, follow the flow. And during these movements, the water becomes older because the age will increase and the oxygen will consume, the AOU will increase because respiration is happening. And in these processes, we get this plot. So the x-axis is the age and the y-axis is AOU. We know that and then we get these plots. At the beginning, the slope is kind of more steep because we have. Oh, sorry. This blue ball is not very clear. It's organic matter. So in the surface, in the upper ocean, we have a lot of organic matter. In the deeper part, we have less. And at the young waters, which is in the shallow part, the slope is steep because we have a lot of organic matter. The respiration is large. And with older water, which is deeper part, we have less oxygen. But overall, it gives some information about the respirations. But the real oceans not only have advection, we also have diffusions, which means the box is not isolated. It's not the simplest way. It's like the box, the AOU and the age were lost to the surrounding boxes. And which means the local age and local AOU might be modified already with these diffusions. And the real ocean is more complex. We have the literal mixing. So the real ocean is not like a 2-dimensional, it's 3-dimensional. So these isopicanals also have this literal mixing, which will introduce the age and the AOU from information outside of the research sections, which might also significantly modify the relationship of AOU and the age. So we have to give the question mark to this age and AOU, whether how this process will modify this age and AOU relationship, and whether in this complex scenario, whether we still a complex but realistic scenario, so whether OUR is able to correctly give the respiration rates, or how much the uncertainty is. And at the beginning, as I said, we want to know whether we can get the oxygen consumption rate trend to better understanding the deoxygenation processes. We have to consider climate change as well. So with climate change, the local respiration will changes, but the literal mixing also will changes, perhaps will also changes the advection, the diffusion, that also changes. So whether under climate change scenario, whether OUR is a good proxy to give the trend of the respiration as well. So that is a question. And to explore this question, we use the models, because in the models we have the ground truth, we have the good reference for the OUR. and I will introduce later. So we explore this question in an Earth system model called FORSI. It is an Earth system model, including a lot of components: the atmosphere, the ocean circulation, the land and sea ice, and of course the biogeochemical processes. And this model is kind of in high resolution, it's half degree. For an Earth system model, is kind of high resolution. We have 46 layers in depth. And to calculate OUR, we have to introduce the age traces. We do not simulate the CFCs or SF6 traces and then calculate TDDs that is usually happen in the real ocean. We have the ideal age tracer. So we exactly measure the time since the water particles leave the surface. So the ideal age traces, like we put a lot of clocks into the ocean. And when it is in the surface, the clock is closed. When it leaves the surface, it open and measure how long it leaves the surface. So it's very very novel tracer we use in the model. And then we need to have the reference, which is I refer to the true respiration rates. But here, true respiration rates does not mean any properties in the real ocean. It's just true in the model ocean. That is the ground truth of OUR in the model ocean. So, and it is calculated in a very simple way. So the local true respiration rate is only from degradation of detritus and the degradation of dissolved organic matter. And this decay rate, we do not consider the temperature impacts on this decay rate as well. So it's a very simple model. This is very simple way to simulate the oxygen consumption. So we have the models. We need to find the research regions, and so here I show the plots of the distribution of ideal age and AOU outcrops and research sections on several asymptotic surfaces. And we follow some criteria that used by some field studies. So we select the regions where the isolates of the age and AOU are parallel, which means follow the age increase and AOU increase, which is exactly follow the concepts of the OUR, which is the water becoming older and the more oxygen is consumed. And also we select the sections which is approximately follow the flow. We follow through following the flow, we try to reduce the literal mixing effects. Of course, it's hard to select the sections that follow the flow at every subpigments, but we try to select. And then we select also the sections that are perpendicular to the isolants of the age and AOU. Again, that is to constrain that we do not have lots of mixing of end members. At least it's a way to go, but it might not be very useful. But that is one of the way to go. And then I select these two sections. One is in the North Atlantic, one is in the South Atlantic. I just name these two sections in one simple way. So the one in the North Atlantic is North Atlantic section. The one in the South Atlantic is South Atlantic section. And then I do some calculations. So I have simulations, which one is ESM PI control simulations, one is in the transient, one is transient simulations. Both simulations have 250 years. That is from 1850 to the end of this century. And ESM PI control means we do not consider any anthropogenic effects. We do not consider human activities. And the transient means we're considering the carbon dioxide emissions from human activities. And in these transient simulations, we use the high carbon dioxide scenario, which makes the local respiration rate signal is more clear. And then we have the simulations. Because the model is in that coordinate, we have to transfer from that coordinate to the isopycnus or potential density coordinates. We calculate and we do this process by using the potential temperature salinity. We give we remap all the variables, and on this sigma coordinates, we calculate the OUR, we calculate the mean true respiration rates along in these density surfaces. We also calculate the depths, the mean depths at these density surfaces in research sections. Afterwards, we calculate the OUR and true respiration integral from 200 meters to 1,000 meters. That is defined as the mesopelagic zone. And then we do the analysis. And here are some results. So here's a result of the North Atlantic section. So in this figure, I show the 200 meters to 1,000 meter integrated OUR and the true respirations. True respiration integral is in red color. The OUR is in the blue color. You see there's some the thick lines is the transient simulations, and the background, the dashed lines is the PI control, ES and PI control simulations. We can easily find that the integrated OUR is just approximately half of the integrated true respiration rates. There have some significant difference. Another thing we can find is both OUR and true respiration decrease following the under changing and with climate change. And to identify what's why we have these differences, we have to plot a vertical distribution of the OUR and the true respirations here. Again, the blue is OUR and red is true respiration rate. And this shading color is the standard deviation. And you can see that the OUR is systematically smaller than true respiration rate over the whole water column, but most of the difference occur in the upper ocean. The upper ocean will have relatively large differences, but below 600 meters we have relatively small differences. What is the reasons for this very large underestimate of very large difference between OUR and true respiration rate? Again, I show this schematic plot. So that is because the OUR is calculated from preserved AOU and age, and not all the AOU, not all the imprints of respiration is stored in the AOU. For example, we have the ERC gas exchange near the outcrops, and exactly near the outcrops, because it's shallow, we have lots of organic matter here. The respiration is very large, but you can hardly see it in the AOU because AOU were lost to the atmosphere, or the lots of oxygen will compensate the AOU. So we hardly see the respiration induced AOU here. And that is a very simple reason. So oxygen flux from atmosphere to the ocean lead to very poor preserved imprints of respiration, which is AOU. So diffusions and advections, you cannot do that, but diffusions you can lead to this very large this poor preserved AOU. And maybe there's some literal mixing. Sorry, the letter is wrong. But literal mixing also maybe also contribute to this, but it's hard to identify this. And then I show the climate change signal by doing transient manners ESM PI control, which is the simulation with anthropogenic effects minus the simulation without anthropogenic effects. By doing this, we isolate the climate change signal. And the plot, the results is quite encouraging in the North Atlantic section. So the integrated true respiration rate changes by about minus 0.87 millimole per square meter per square year, because we do the trend of respiration rates, so the changes of respiration rates. So we have double time here, and this plus minus gives the 95 confidence intervals. So this is the statistic values from this true respiration time series, and the integrated OUR changes by a very similar trend. And then these two values are overlapped at 95 confidence intervals as well, which statistically we can see that OUR is able to track the long-term trend of true respirations. And the correlation coefficient between OUR and true respiration rate is 0.5. It's not very bad, I think. And then the conclusion is the integrated OUR is able to track the trend of integrated true respiration rates in the North Atlantic section. However, that is not the case in the South Atlantic, where the dynamics of the water masses in the South Atlantic is very complex. Here again, I show the similar things. The integrated true respiration is similar with integrated OUR. If you see the red line and the blue line is very similar, the values, but the integrated true respiration decrease, so the red line decrease, and AOU increases, the blue line increases. It's this diverging trend with climate change. And even though the mesopelagic integrated OUR have the similar value with the integrated true respirations, the vertical pattern is very different. The OUR shows very complicated vertical patterns. It first decrease and then increase from 300 meters to around 400 meters and then decrease again. And true respiration always decrease, following almost the power law of the depth. So which means, even though overall the integrated OUR works well, but we cannot say that OUR is a good proxy of local respirations. And the reasons for this complex vertical patterns of OUR might be the mixing, the literal mixing, which induce the age and AOU from the waters with different biogeochemical history. So at least it induces the age and AOU and destroy the age and AOU relationship that induced by the local processes. But it's hard to prove this in a straightforward way. So we assume that is the reason. And again, to see the climate change signal, the true respiration decrease with kind of a large values, minus 1.3 millimole per square meter per square year. And the OUR increase very dramatically under changing climate. And the correlation coefficient is negative and it's very low, which means the OUR have very poor relationship between the local respirations. So it's, which means OUR might not be a good proxy in this South Atlantic section. And the integrated OUR shows opposite trend with integrated true respirations. That if you, that means the OUR even cannot give the correct sign of the true respiration changes under changing climate. And conclusions, the OUR integral have potential ability to reconstruct the respiration rates integral in parts of the mesopelagic ocean. That is, for example, in the North Atlantic Ocean, where we have relatively simple core waters. And that is a region we have abundant CFC environments, abundant oxygen environments. So it's a good, it's a positive news. However, that is not the case in other parts of the ocean. So the temperature trend diagnosed from OUR can be a very unreliable indicator for the trends in true respiration. That is, for example, in the South Atlantic, where the OUR increase, that does not mean that the true respiration also increase under changing climate. The reason is because OUR contains not only the local respiration information, but also the mixing information that from the mixing of different end members. So these books, for example, the books from location 1 to location 1, the books is not isolated. It has the exchange with surrounding waters. If we want to use OUR to assess the changes in aerobic respiration, we need accurate knowledge of the mixing induced H and AOU and remove them if possible. However, that in a transient ocean is a hard way. I think it's difficult. At least to my knowledge, there's no papers or method that try to solve this problem in the transient ocean. In a steady state ocean, it's a way to do it, but in the transient ocean, it's very difficult. So I give the question mark to this OUR mixing. And then, yes, that's all the information that I can show, and I'm open for any questions.
Yeah, thank you very much, Haichao, for your very enlightening presentation. I'll stop the recording.